So the lecture for today is igneous rocks and volcanoes. So the reason these two are linked together, lumped together, as it turns out, igneous rocks and volcanoes are associated with one thing, and that's called magma. So magma is the source for all igneous rocks, and igneous rocks can come to the surface in the form of volcanic explosions, volcanic rocks, volcanic lava flows. When magma comes to the surface, we refer to that as lava. So the difference between magma and lava is that lava is at the surface, magma is under the ground. If that magma crystallizes underground, which it often does, it'll form what we call crystalline rocks. If that magma comes to the surface, it does not crystallize, it cools too quickly, and it forms non-crystalline rocks. So as it turns out, igneous rocks that are crystalline, igneous rocks that are non-crystalline, all originate from magma. Magma we see at the surface in the form of volcanoes. So environments. As it turns out, there's two basic types of igneous rocks. There are intrusive rocks. These are rocks that form under the ground. And the difference between intrusive rocks and extrusive rocks that we see at the surface is that intrusive rocks form under the ground and they form inside the earth, and they take a very long time to cool down. And because of that long cooling period, these rocks form minerals, visible crystals. So granitic rocks that we see at the surface, like a Big Bear, those rocks at one time were thousands of feet underground, and they've since then been uplifted due to tectonics. So extrusive rocks, they form at the surface, they cool so quickly that they don't have time to form crystals, and they have just a ground mass that you really can't identify individual crystals of. And that's the difference between the two rocks. So intrusive and extrusive igneous rocks. Intrusive examples, rocks that form under the ground, are granites, which is a very light colored rock. Gabbro is a very dark colored rock, crystalline. And then an intermediate rock, which is kind of half light and half dark, is a diorite. So what's the difference between gabbro and granite? Is that the magmas are different. Gabbro is high temperature magma. It has high temperature minerals. Those minerals, because they're high temperature, tend to be rich in iron. And iron minerals form very dark rocks. So gabbro is a very dark rock. People who sell countertops refer to this as black granite. There's no really such thing as a black granite. It's a gabbro. Where granites tend to be very light colored, pinks and tans and white. And they're rich in quartz, and they're lower temperature. And then in the middle there, between the high temperature and the low temperature, the high temperature rich in iron and the low temperature rich in quartz, is the intermediate rock called diorite. And that's a rock that consists about 50% of it is quartz rich and 50% of it is iron rich. So extrusive rocks are the same: rhyolites, basalts, and andesites. So a rhyolite and a granite are basically the same rock chemically. They're both low temperature, they're both rich in quartz. The difference is the rhyolite forms at the surface and the granite forms underground and forms crystals. So crystalline rock, non-crystalline rock. And I have some really good pictures that show those two together. And then gabbros are high temperature rocks that form under the ground. And at the surface, those high temperature rocks are what we call basalt. So the difference between a basalt and a gabbro is basalts have no crystals to them. They're just a black rock, where gabbro is a black crystalline rock. You can see the individual crystals. And again, the difference between the intermediate, the andesite, and the diorite is what I call the 50-50 rock. Half that rock consists of white minerals, the other half consists of black minerals. And you can actually see those, where in the andesite you can't see the minerals. It's all just mixed together, it's all gray. So all three of these extrusives are equivalent to these intrusives. So a granite and a rhyolite are the same rock. They're both low temperature. This has crystals in it, this does not. Basalt and gabbro are both high temperature rocks, lots of iron in high temperature rocks. Those rocks form in different environments, that's why they're different appearance to them. The gabbro forms under the ground, very crystalline, and the basalt forms above ground, does not have time to cool. So here's a good example of a granite, very light colored rock. This would be a little more darker rock incorporated within it. That'd be like a gabbro, and this would be a granite. So you can see there's a big distinctive difference between the two. What's the difference between these two rocks is temperature. This formed a little higher magma temperature. This formed a much lower, like 600 degrees Celsius versus 900 degrees Celsius. So granites that are rich in quartz tend to be light colored. These are what we call felsic rocks, and the word felsic is a Greek word that comes from feldspars. And a good example of one of those feldspar is a pink feldspar called potassium feldspar. So granites, we find them all over the surface, but yet these rocks at one time formed thousands of feet below the ground. They crystallized over long periods of time. Since then they've been uplifted. So some of the most spectacular landscapes throughout Earth are granitic rocks. So this is the Sawtooth Mountain Range. This is right on the entrance to Yellowstone National Park. These rocks are granitic. They're crystalline. They were formed underground. And then since then, due to tectonics and mountain building and uplifting, these rocks have been uplifted to their current position. And now they've been subject to the forces of weathering. A lot of glaciations have carved out these little valleys here, creating this little sawtooth look here. The Sierra Nevada mountains, which are one of the main backbone of the mountain chain within the state of California, are also granites that formed underground. This is a combination. So Sierra Nevada mountains really continues into the south part of California. We know it as the San Gabriel and the San Bernardino mountains. Those mountains were all once part of a huge, great big mountain chain that has been since then been segregated by the San Andreas Fault. Very tip of southern Baja Peninsula is Cabo San Lucas, and this seems like it's a little bit out of focus. I hope that it's just we're dealing with an older projector here. There's a little bit better focus. So the very southern tip of Cabo San Lucas, these are all granitic rocks. They're crystalline. They've got visible crystals. This is light colored, it's rich in quartz. So these are definitely granites. Again, these formed thousands of feet below the surface. And due to tectonics, when the Baja Peninsula was formed, these rocks were uplifted. So rocks that form underground, they cool very slowly. They can form crystals. It's when these rocks that come to the surface in the form of volcanoes that they're exposed to the atmospheric conditions, rain, and just lower temperatures. And the result is they cool quickly and they don't form crystals. Magma bodies are different. So there are some magma bodies that are higher temperature and they're rich in iron. Other magma bodies are lower in temperature and they're rich in quartz. And sometimes these magma bodies mix together and they can form an intermediate. So it's amazing. There's a lot of things that we probably have more questions about this magma and this interaction deep within the earth than we actually have absolute answers. So there's a lot more questions out there. The geochemical aspects of magma is you can actually, there's a subdiscipline in geology called geochemistry. And geochemists look at rocks and they try and figure out the chemical differences and the temperature pressure changes that result in these different rocks. And that's a blank screen, which I don't know why that's happening. So one way that we see volcanoes is we talk about plate tectonics. So this is a good example of a divergent plate boundary. So right there in the middle of the Atlantic Ocean and out in the Pacific Ocean, there are these spreading centers where new rock is being added. So this new rock is being added, it pushes the old rock aside, convection, the driving force for plate tectonics. So every place where we add an inch of crust on Earth, we get rid of another inch someplace else, and this is all due to subduction. As this plate subducts, it's going to melt. As it melts and becomes exposed to higher and higher temperatures, the deeper you go into the earth, the warmer it gets. This rock is going to melt, and because it melts, it's going to be less dense. It's going to rise to the surface in the form of volcanoes, and we see these chains of volcanoes all around the globe, and these volcanoes are generally associated with plate boundaries. So if we look at the distribution of volcanoes, we see that those volcanoes certainly follow plate boundaries. So this is a good example of the Ring of Fire around the Pacific Plate. We have a chain of volcanoes all around South America, on the west coast of South America, up through Central America. In our part of the world, in California, Oregon, Washington, we have the Cascade Mountain ranges, which starts with Mount Shasta in California, goes all the way up to Mount Baker on the border of Canada and Washington State. And so we see these volcanoes all around, and this is because plates are being subducted and materials come into the surface. And so these volcanoes are all examples of extrusive igneous rocks. This is where we're going to find rocks like basalt, andesite, rhyolite. The rocks that are forming underneath these volcanoes are going to be the granites and the diorites, depending on the composition of the magma, if it's rich in quartz or rich in iron. So explosive volcanoes and mild volcanoes. So there's two types of volcanoes. There are volcanoes that are very explosive, like Krakatoa, Mount St. Helens. And then there are volcanoes that are more mild, such as the Big Island in Hawaii. This is a lava flow where geologists walk right up to Hawaii during an eruption. And they film it, and they actually take samples of the lava. You could not do that at Mount St. Helens because of the explosive nature. So what makes the difference between volcanoes that go boom and volcanoes that are mild is what's in the magma. So as it turns out, the lower temperature volcanoes, the ones that are rich in quartz, tend to be very explosive. And the reason for that is that the silicates, the silica, SiO2, in that magma tends to crystallize, and it's very sticky, and it clogs up the vents of volcanoes. It clogs up the necks where that magma wants to escape and become lava. And so these volcanoes tend to build a lot of pressure. On the other hand, the magma that is high in iron, which is a higher temperature, flows more like a liquid. And they don't clog up, and they're not as explosive. So any volcanic eruption, if you're living near any volcano, it can be bad for you, but obviously there's a huge difference between the way Hawaii erupts and the way Mount St. Helens erupted. So here's a good example of a lava. It was once magma, and it's come to the surface. This is very dark, so it's rich in iron. This is high temperature, and this is a geologist, a volcanologist, Charles Fletcher, who was actually sampling the lava. You can do that in Hawaii because these eruptions are fairly mild. And as it turns out, in Hawaii, there's two types of lava. There's the pahoehoe, which flows out, and there's the stuff that consists of air holes. But again, these volcanic eruptions are fairly mild. You can walk up and just see the eruption, and you can see the magma as it cools, and it gets this pahoehoe look to it. And this is because the surface cools first because it's exposed to the atmosphere, and then underneath it's still liquid, and the liquid's still moving, but the top is crusting, getting hard, so it doesn't want to flow, and you get this little ripple effect of this lava. So in Hawaii, the volcanoes are very mild, and that's because they're high temperature, high in iron, and these are going to be very dark rocks, going to form a dark black rock called basalt. Explosive volcanoes, we find these on continents. So remember a couple weeks ago when we talked about plate tectonics, there are basically two types of plates. There's oceanic plates, which are rich in basalt. Basalt is rich in iron. And then there's continental crust, which is rich in silica or quartz. That's why continents tend to float, and ocean basins where the basaltic rock are wind up forming very low topographical areas because that magma, which is rich in iron, is more dense, and it compresses and it forms topographically low areas, and that's where water goes. So oceans are found around basaltic rock, and then in continents we have very rich rocks that are white and pinks, and these are rich in quartz. So continental volcanoes tend to be very explosive, and they have a lot more larger variety of rocks. So they have things like pumice, obsidian, andesite, rhyolite. This magma composition is very sticky. It's like syrup on a cold day. It will not flow, and as a result, these inner piping, the inner plumbing of volcanoes has a tendency to clog, and it builds pressure, and that's exactly what happened with Mount St. Helens, is that Mount St. Helens, so much pressure built up that Mount St. Helens started to bulge on one side, and then all that magma started to escape out to the side there, and then there was a landslide that took that bulge away, and that volcano basically erupted outward in a lateral explosion. So this is a typical continental volcano. These are very steep, but they're very small volcanoes in comparison to the Hawaiian Islands. So Hawaii is the largest mountain on Earth if you count from the bottom of the ocean to the top. Now, the way we record elevations throughout the world is we use sea level as the base. So sea level is 0 degree, is 0 feet in elevation, or 0 meters, depending on where you're at, or what unit you're using to measure it. So if you're standing there right at sea level, you're at 0 elevation. And as we move up into the mountains like Big Bear, you increase in elevation to 6,000 feet, 8,000 feet, and so forth. And so we record mountains based on their elevation from sea level up. But if you look at the big island of Hawaii, most of it's underwater. So it's much larger in comparison to the Himalayan mountains, but the Himalayan mountains are being measured from sea level up. So these types of volcanoes, these continental volcanoes, because they're lower temperature and they're higher in quartz, this magma tends to be very viscous, it's very volatile. There's a lot of gases involved in this, a lot of water vapor, a lot of carbon dioxide. Volcanoes emit a tremendous amount of carbon dioxide in the atmosphere, and these tend to be very explosive volcanoes. So interesting enough is that predicting volcanoes like Mount St. Helens is a real problem, because you don't know what that magma body coming up is like. It could be a high temperature magma body, rich in iron, and it's going to flow out like Hawaii. Or it could be a lower temperature magma body, rich in quartz, and it's going to be very explosive. Or it could be an intermediate, half quartz, half iron. And this is why predictability of volcanoes, especially on the continents, is really a problem. So there's basically 2 types of volcanoes. There's shield volcanoes. Now, some books list 6 different volcanoes. And if you're really into volcanology, into volcanoes, you'll classify every type of the volcanoes. We're going to look at basically 2 types. We're going to look at shield volcanoes and composite. Composite are also known as strata. They're also known as continental. So they have a lot of words for the composite volcanoes. But certainly the shield volcanoes are Hawaii. This is a basaltic rock that's rich in iron and magnesium. Very high temperature. Very dark rocks, but they flow out. Where the composite volcanoes, the strata volcanoes, or the continental volcanoes that you find on continents, these tend to be very explosive because of the quartz content. So there's all different classifications of volcanoes. We're going to basically look at the shield volcanoes, which you see in Hawaii, and what we call the stratovolcanoes. Mount St. Helens is a good example of a stratovolcano. Mount Rainier, Mount Hood, Mount Baker, Mount Shasta are good examples of stratovolcanoes. And then basically a cinder cone. We have a lot of these in California. These are just smaller versions of stratovolcanoes. So shield volcanoes, the largest mountains on Earth are shield volcanoes. If you measure from the bottom of the sea to the top, and this magma is very rich in iron, and that's why it produces that dark rock. So remember, dark equals high temperature, dark equals iron. Light equals low temperature quartz, very high in silica. So here's a good example of the Hawaiian volcano. I actually took this picture at the Hawaii National Park. This is the visitor center. These are so huge. I mean, they continue onwards and then they go underneath the ocean. So these stratovolcanoes are small compared to this volcano, this shield volcano. So shield volcanoes are huge. So Mount St. Helens, you could put 100 little Mount St. Helens in this area. I mean, Mount St. Helens is relatively a small volcano in comparison to the big shield volcano that makes up Hawaii. And what we know about this is that underneath Hawaii, there's a hot spot. So this is high temperature magma. And as it's high temperature magma, it's going to bring up iron rich. So you're never going to see a granite forming in Hawaii. You're never going to see rhyolite or obsidian or any of those types of rocks, because those are quartz rich, low temperature. Hawaii is very high temperature. And like I said, the lava just flows out. You can actually go up and take pictures of it. People go visit it while volcanoes are erupting. You couldn't do that with Mount St. Helens because you'd be buried. And people were buried in that particular volcanic eruption. So composite, continental, or stratovolcanoes, I should put strata in here too. The magma is very high in quartz, silica, SiO2, and this produces rocks like rhyolite, pumice, the rock that floats, obsidian, which is volcanic glass. Native Americans use that to make arrowheads and scrapers. And the volcanic tuff is basically the ash that comes out of volcanoes. Very explosive, very volatile. And these are very steep volcanoes, where the shield volcanoes tend to be more dome-like, much larger. So Mount St. Helens erupted in 1980, and geologists flocked from all over the world when the earthquakes started occurring, and they realized that magma was moving up into the chambers of Mount St. Helens. And interesting enough, they really didn't know what type of eruption it was going to be. They didn't know what the magma composition was. They didn't know if it was rich in iron or rich in quartz. As it turns out, this magma body was very rich in quartz. This volcano clogged up. It created a bulge on one side, and then it exploded in a very catastrophic explosion. The volcano erupted and wiped out everything for 25 miles. Knocked down trees. So this is a photograph that shows the volcanic cloud. I know it looks soft, doesn't it? It looks like a pillow. But this is high temperature. It's like, 500 degrees Celsius. Anything that's in here is just vaporized instantly. Look at the foliage on the trees. And this is after that ash has passed, that volcanic eruption, that pyroclastic flow. This is what's left of the forest. Looks like a box of toothpicks that somebody dropped out. A lot of equipment got moved around. And like I said, there was a blast zone for 25 miles. There were geologists who were camped about 6 miles from the volcano, and they thought they were safe. And unfortunately, that was a huge error, and photographers were killed when Mount St. Helens erupted. So this is what happens to Mount St. Helens in one catastrophic event. This big mountain, all this area here was ejected in one catastrophic explosion. So these continental volcanoes, these quartz-rich volcanoes, are very volatile. They're very explosive. And we find evidence in like the Mojave Desert. This is actually at Lake Mead National Recreation Area. And here in the desert we find a lot of this rhyolite rock, so that would be indications of very explosive volcanoes. And then right on top here is a lava flow. This would have been a very mild eruption, like Hawaii. And so this is where predicting volcanoes is a problem. Hawaii, we know, it's always going to be rich in iron because it's high temperature. But Mount St. Helens and continental volcanoes such as Mount Lassen, Mount Rainier, Mount Baker, even Mount Shasta, they will erupt again. We just don't know when. And we don't know what the composition of the magma will be until it comes to the surface. We have no way of going inside the earth and finding out chemically what's in that magma. It's just, science isn't there yet. Around the deserts, the Mojave Desert, this is actually out in the Mojave Desert near the lava tubes near Barstow, between Barstow and Ludlow off of I-40. So this is a very flowing type of lava, very rich in iron. So there's two cinder cones out in the Mojave Desert, not too far from Interstate 40. One is Amboy, and these volcanoes erupted within the last probably 1,000 years. There's a lot of studies are occurring as far as how they dated these rocks. And you have to realize that this was an iron-rich eruption, and this has been a very mild eruption, but yet you find other rocks in the same area that are indications of very explosive volcanoes. So here, this is actually near Calico Ghost Town off of Interstate 15, just to the east of Barstow. This is all rhyolites and andesites. This would have been very explosive volcanoes. What's neat about volcanoes, and one of the things that is great for the state of California, is a lot of our mineral wealth, such as the silver deposits at Calico Ghost Town. Those silver deposits were deposited because of volcanic rocks. So volcanoes certainly bring up a lot of minerals too, valuable minerals such as metals of gold and silver, which really helps aid in the economic wealth of the state of California. So let's look at igneous rocks now. So look at volcanoes. Igneous rocks, there are igneous rocks that form underground. These rocks have a long time to cool, and they form crystals. An igneous rock that is crystalline can be a dark colored rock, it can be intermediate, half and half, or it can be light. So it can be quartz rich, half quartz, half iron, or iron rich. It's not the composition of the magma that so much plays the part in the crystalline rocks. it is basically the place where it forms. So in the case of igneous rocks that form underground, below ground, we call these intrusive rocks. So below ground, the magma coals forms granitic rocks, diorite, and gravel. And they're referred to gravel sometimes as a black granite. Slow cooling, they form visible crystals. Minerals often referred to as crystalline rocks, so we call these crystalline rocks. The extrusive rocks, above ground, quick cooling, they do not have time to form visible minerals. So these form far too quickly for the minerals to get together and to form geometric shapes and individual crystals. So the type of rocks that we're going to see out of these volcanic rocks are going to be things like basalt, that's an iron-rich rock. Rhyolite is a quartz-rich rock. Asphalt tuff, volcanic tuffs are also quartz-rich. And obsidian and volcanic glass is also quartz-rich. Obsidian is black though, and this throws a lot of people off. And the reason that obsidian is black is 98% of the obsidian is quartz, but just a little bit of iron got in there to make it dark. So that's is why people get thrown off here when they see obsidian. It's really volcanic glass. Whoop, looks like I'm going too quick here. Okay. All right. So like I said, the extrusive rocks that form out of Hawaii, high temperature, very iron rich, and they form rocks like the hoi hoi, the Ropi basalts, and they form the A'a lava, which is a lava that had a little more volatiles in it, a little more gas, water vapor, and as those vapors escaped, they escaped into the atmosphere, creating a pathway of holes, and that's why these rocks are full of holes. It's also referred to as lava rock. So silica is very viscous, it's very sticky, it builds a lot of pressure, it clogs those volcanic pipes, and this is why those types of volcanoes erupt. So composite volcanoes, stratovolcanoes are very explosive because of the quartz content. So these composite volcanoes, they're explosive because of the silica. So I kind of repeated this because I really want you to understand the difference between iron-rich and silica-rich. So this looks like, this is Mount St. Helens after the 1980 eruption. And throughout the Mojave Desert, you find areas where you find very dark igneous rocks, like such as this place called Lava Butte. That would have been a very mild eruption. And then you find all this volcanic ash. That would have been a very explosive eruption. So this is why predicting volcanoes on continents is a problem, because we don't know what that composition of that magma is. And one volcano one time will basically produce basaltic rock, very mild eruption. The next eruption might be very explosive, rich in quartz. Then there's volcanoes that don't quite fit this. Yeah, we have Hawaii. It's shield, rich in iron, high temperature. And then we have the continental volcanoes that tend to be very rich in quartz. And then we have Iceland. So Iceland sits right on the Mid-Atlantic Ridge. So it's a part of the Mid-Atlantic Ridge that's actually above sea level. It also sits on a hot spot like Hawaii. So that's why Iceland is there. And the rest of the volcanoes along the Mid-Atlantic Ridge are underwater. And it's very unique. Whoops, something's going on here. I don't know why this is doing this. But Iceland, it sits right on a plate boundary between the North American plate and the Eurasian plate. So that's Iceland. And Iceland has 5 very dangerous volcanoes. And one of them erupted in 2010, which actually impacted climate throughout the summer of 2010 in Europe and even throughout the United States. We had a very cool summer that year, and that was because of all the ejectile material that came out of Eyjafjallajökull, a volcano in Iceland that erupted. So here is a map of Iceland. Eyjafjallajökull erupted in 2010. It sent ash, which blanketed over the United Kingdom, Europe, which is in a very cool summer. This has happened in the past. Benjamin Franklin wrote about a very cool summer in Europe due to a lot of haze in the air, and that was probably the eruption of one of the volcanoes in Iceland. So it's amazing how one volcanic eruption can impact our life. So Eyjafjallajökull and the other volcanoes that make up Iceland will erupt again. It's just a matter of time. So Iceland sits right on this rift valley between two plates. So if you live on the west side of Iceland, you're moving to the west. If you live on the east side of the island, you're moving to the east towards Europe. So Iceland is actually growing in the middle, getting larger as time goes. All right, so igneous rocks. There are dark igneous rocks, there are intermediate igneous rocks, and there are light-colored igneous rocks. And so both a dark rock made of iron or a light rock made of quartz, either one of those can form underground. When they crystallize into the ground, they're actually going to form crystals. If it's rich in iron, it's going to form dark crystals. If it's rich in quartz, it's going to form light-colored crystals. And that's the difference between, really, the dark and the light, or felsic rocks. And an intermediate is really a combination of magma that's rich in iron and magma that's rich in silica. So you can have a quartz-rich rock form underground, and that's going to form granite. If that quartz-rich magma comes to the surface, it's going to cool very quickly, and it's going to form a rhyolite. And I have some pictures that'll show that. So igneous rocks. Remember, there's two types of crust: oceans and continents. Oceans are rich in basalt, higher in iron. Continents are lighter, more buoyant rocks. They're rich in quartz and feldspars. So silica plays a big part in those particular rocks. They're lower temperature too. So let's look at intrusive igneous rocks. They solidify, they cool underground, long periods of cooling, and this allows for the growth of minerals and crystals. So these are rocks that form underground. This allows crystals to interlock and grow together. So igneous rocks form as molten rocks and then cools and solidifies first. So this actually makes a good quiz question. What is the parent of all igneous rocks? And that is simply magma. So the crystallization of magma, it depends on what this parent material is. If that material is rich in iron, it's going to form a dark crystalline rock. If that parent magma is rich in quartz, it's going to form a light colored rock. All right, so let's look at basalts and gabbro. Basalt and gabbro have one thing in common. They're both rich in iron. They both come from high temperature magmas. But the difference is that basalt forms at the surface. We call that extrusive. Gabbro forms underground. We call that intrusive. So extrusive is basalt, intrusive is the gabbro. The gabbro forms lots of time to cool. We call these sometimes called plutonic rocks. So plutonic rocks means they're magma chambers that cool underground. We refer to rocks that are rich in iron as mafic rocks. So mafic is a word that simply means rich in iron, mafic. Ferromagnesium. Rocks that are light in color, we call those felsic, for feldspars. So Nate, what's in magma? Well, there's three components. There's the liquid portion, which is the melted rock. Then there's the solids, as that rock starts to crystallize. And then there's the volatiles, which are gases, such as water. A lot of water vapor in volcanic clouds. A lot of CO2, carbon dioxide. So volcanoes emit carbon dioxide all the time. In fact, volcanoes are probably the greatest modifiers of climate on Earth, natural climate modifiers. They can make the Earth either warmer by emitting tons of CO2, or they can make the Earth cooler by emitting lots of ash, which blankets the Earth, that reflects incoming solar radiation. And there's other volatile gases such as sulfur dioxide. As it turns out, right before volcanoes erupt, they emit a lot of sulfur dioxide, SO2. As the magma chambers are deeper, and the volcano's not really getting ready to erupt, they emit lots of carbon dioxide. So most of the volcanoes around the world today, around Earth, are emitting CO2 in the atmosphere. They're still active, but they're like in a dormant stage. And even in their dormancy period, they emit tons of carbon dioxide into the atmosphere. So there's crystallization of magma. So what happens is this magma, as it cools, lowers in temperature, that iron and that silica are going to crystallize. They're going to actually form crystals, and those crystalline structures are going to combine to form igneous rocks. So they form in a very predictable order. All this predictable order is saying is that the high temperature minerals are going to come out last. So if a magma body comes up and it's 1200 degrees Celsius, as that magma body cools down to say 900 degrees, the first minerals that are going to form are going to be the iron-rich minerals. The iron-rich minerals. And then as that magma continues to cool and gets down to 600 degrees, then the quartz-rich minerals are going to form. And then sometimes these magma bodies will do a little bit of mixing too. So to identify igneous rocks, we look at two properties. We look at color, dark or light or intermediate, and we look at texture. So when you identify igneous rocks, you look at two aspects: color and texture. So what is texture? Visible minerals or non-visible minerals. So if the rock has visible minerals and those minerals are big, that tells you this rock cooled very slowly. If that rock has very fine crystals, then it formed fairly quickly. If it has no crystals in the structure to it whatsoever, that means it almost cooled instantaneously as it came out of the ground. And so this is the two things we look at when we identify igneous rocks. We look at color and we look at texture. So temperature is used to describe the overall conditions of the minerals as they form. So high temperature minerals tend to be rich in iron. Low temperature minerals are rich in quartz. So the factors that affect the size of the minerals are going to be basically the rate in which they cool. And so if they cool very slow, you can have very few but very large crystals. So that's very, very slow. A rock that cools very fast, many small crystals. And the quickest rate of cooling is so as it can form glass. And the rock that has the fastest rate of cooling is obsidian. So here are two rocks. One's extrusive and one's intrusive. They're both rich in iron. So the magma body that these two rocks came from was a high temperature magma body. This magma body is very rich in iron. The basaltic rock has no crystalline structure to it. It's what we call an aphanitic texture. This rock here is a phaneric texture. We can actually see the visible minerals. Now it's hard to see in a dark rock like that. Here, this rock formed above the ground, aphanitic texture. This rock formed below the ground, phaneric texture. So you can look at by this rock here, this granitic rock. You can see that there's some pink material in here, black material, and white material. So these are three distinct minerals that crystallized because this rock cooled very slowly. And this is what we call phaneric texture. So phaneric means visible minerals. You can actually see these minerals. So this granite formed fairly slowly. On the other hand, this was an extrusive rock that came to the surface and cooled very quickly, and there are no really visible minerals. I mean, you could slice it into a thin section and look at it under a high powerful microscope, and then you'd be able to see the crystalline structure. But to the unaided eye, there is no crystalline structure in this rock, and there is in this rock. And that's the difference between the two. So phaneric means underground, slow cooling, lots of time for the crystals to grow. The aphanitic crystalline means very quick cooling, no really visible crystals. Obsidian, it forms so quickly that it is basically glass. Now the reason that obsidian has this glass look is because it is glass. The mineral content, the chemistry of this rock is 98% quartz. A little bit of iron got in there and can make it into a black obsidian. There's also a brown obsidian, and that was influenced by potassium feldspar, which makes it kind of a brownish color. And then this is a rock that cooled very slowly, pegmatites. So pegmatites are rocks that cool very slowly. How slow? We think theoretically on the terms of millions of years. So millions of years of cooling time. These rocks have plenty of time to grow, and they grow very beautiful crystals. And so this is what we call a pegmatite. Extrusive rocks, the absolute opposite, 180 degrees, comes out to the surface, instantaneously crystallizes, doesn't have time to form crystals because of that time factor. So the importance of color. Color is really important. I've talked about this. So iron-rich rocks are going to be dark. Quartz-rich rocks are going to be rich in silica. So igneous rocks are composed primarily of silicate minerals. Dark we call mafic. Ferromagnesium, that's iron. Light we call felsic, and this is basically a Greek word meaning feldspars. Feldspars, as it turns out, are very rich in quartz, extremely rich in quartz. So feldspars are very rich in quartz also. And so dark minerals, these are rich in iron. So things like olivine, pyroxene, which is a very dark green rock. Amphibole is a jet black rock. And then the silicates are going to be basically quartz. The micas and the feldspars tend to be light color. So here are two rocks. These are both intrusive. They're both formed under the ground. They have plenty of time to cool. They're both phaneritic, visible minerals. This is a granite, light colored, and this picture doesn't really do it justice. And this is more of a darker gray rock, and this is a gabbro. And so the reason I picked this particular gabbro is that this gabbro is light enough, after you take a picture of it, to show the mineral content. So this has individual minerals on it, so does this. The advantage of the granite is there's such a contrast between the pink potassium feldspar, the clear quartz, and the dark mica, that you actually see a contrast between these two. So what's the difference between these two? Quartz-rich, iron-rich. They both form underground. And then there's an intermediate rock. So this is a rock that has 50% of it is quartz, what we call felsic. 50% of it is mafic, iron-rich. And this is kind of a unique rock. We think this is because two different magma bodies mixed. That an iron-rich magma body from perhaps a subducting seafloor plate intermixed with some of the surrounding quartz-rich rocks, which then changed the composition of the magma from mafic to intermediate. It didn't quite make it to felsic. And this is what we call the intermediate rocks. And the best example of that is diorite. So diorite, this is a rock that formed under the ground. It had a long time to cool. There's two distinct minerals in here. The black stuff is called amphibole, and the white stuff is a white plagioclase. Now if you took this rock and ground it down and put it in a blender and mix it all together, it'd form a gray rock. So intermediate rocks are either going to be gray in color, andesite's a good example of that, or they're going to be this half Oreo McFlurry rock, I call it. It looks like when you go to Dairy Queen, you get the Oreo McFlurry, and they mix the Oreos with the vanilla ice cream, mix it all together. Oreo McFlurry rock, there it goes. And then there are ultramafic rocks. So ultramafic rocks are kind of rare. These are rocks that are rich in a mineral called olivine. And so when Eyjafjallajökull erupted in Iceland in 2010, the first thing the geologists did is they went to Iceland and they were looking for olivine. They were really looking for olivine because if olivine were found in a large concentration in the ash that was coming out of that volcano, that would have meant it was a very deep, deep eruption, that the magma body was coming from deep within the earth. And that would have resulted in a very long-lasting eruption. And volcanoes in Iceland have done this in the past where they've erupted for years. Imagine that. Imagine would that occur today. What would it do to air travel and to everything in Europe? So here's a diorite, an intermediate rock. Underground, intrusive, phaneritic texture. Aphanic texture, no visible minerals. Forms above the surface, cool too quickly. So here's a granite. This is a rock that forms under the ground. Phaneritic texture, felsic, I know these are a lot of strange words. Felsic, phenoric, like you can just go and get those things. And as it turns out, these rocks here are rich in quartz. And then rhyolite is the equivalent of a granite. The difference between a rhyolite and a granite is the rhyolite forms above the surface. It cools quickly. So this is the rhyolite. You don't see visible minerals in this rock the way you do the granite. So this is the extrusive. We call this texture aphanetic. Again, it's light colored because it's very rich in quartz. Very rich in quartz. And you put those two rocks together, this is what they look like. So this is the same magma body. Same composition, same temperature. It both consists of low temperature, 600 degrees Celsius, which is pretty hot, but you know, in comparison to rocks, it's lower. Above ground cools quickly, below ground cools very slowly. And so we have the different textures are the result of the different places and the time allowed from the cool. The color is all due to the fact that these rocks are both quartz rich. And then glassy versus pumice. So both pumice and obsidian are essentially the same rock. The difference between the two is this. Obsidian didn't have a lot of volatiles. It did not have a lot of gases in it. So it's very dark colored. It's glassy. The composition is mostly quartz. But the reason it's dark in color is just enough iron got in there to make it dark. Pumice is also volcanic glass, but it has a frothy appearance. So it's almost like when you pour root beer on top of vanilla ice cream and it frosses up into that foam. That's because of all the volatiles that were all in that obsidian that escaped the gases. So some magma bodies are rich in gases, and that's heavily influenced by the amount of water, especially groundwater. And this gives us a frothy look. So pumice, people use it to scrape calluses off their feet. They use it for an abrasive. It's volcanic glass and has a lot of air holes in it. So this is obsidian. It is a felsic rock, even though it's dark. I know this is one that kind of plays a trick on you. But if you were to flake off obsidian to very thin sheets, you can almost see that it's almost translucent. You can almost see through it. And then pumice is the same thing. The difference is that this is where the volatiles expanded the rock and created all these air holes. And pumice is the only rock that floats in water. Then there's the intermediate composition. There's the andesites and the diorites. These rocks contain half quartz and half iron. So volcanic tuffs, asphalt tuff, excuse me. This is all the material that comes out of volcanoes. So we know from the studies of the ocean floor by Rear Admiral Hess, United States Navy in the 1940s and 1950s, that in the middle of the Atlantic Ocean there's a ridge system. This ridge system is the driving force for plate tectonics because of convection that's adding new rock, pushing that new rock aside. And in the middle of this ridge, this is magma, which is higher in temperature, and it creates basaltic rock. So basaltic rocks, which are rich in iron, are found in ocean basins. And so these magmas can evolve. And so what happens in the crystallization of magma, the minerals crystallize in a systematic fashion based on their melting points. So in other words, some minerals melt at lower temperatures, some minerals melt at higher temperatures. It depends on what's in them. If it's rich in quartz, it's going to melt at a much lower temperature. If it's rich in iron, it's going to melt at a much higher temperature. So as that magma body starts to cool down, the first minerals that are going to crystallize are going to be the minerals that are rich in iron. And then the intermediate minerals that are rich in iron and quartz. And then the very last minerals that are going to crystallize are going to be the quartz-rich minerals. So the Sierra Nevada mountains, if you go to the upper elevation of Sierra Nevada mountains, you'll find granite, light-colored rock rich in quartz. But at the lower parts of the Sierra Nevada mountains, and some of the foothills, you'll find gabbros and diorites. And that's because those minerals, those gabbros, crystallize first. And as they crystallized and they became more dense, they sank. And then the gabbros formed, and they sank. And then after that, when the magma body cooled a little more further, the intermediate rocks. The rocks are half in quartz, half in iron. Those are going to crystallize, the diorites. They're going to form and go to the bottom. And then the last thing, what's in the magma now, is all the low temperature quartz. It's not going to crystallize until that magma body cools down to about 600 degrees Celsius. So this is what's called the Bowen's reaction series. This shows the systematic cooling of minerals, the formation of minerals like olivine, pyroxene, apple. All these minerals, apple, pyroxene, olivine, and calcium plagioclase, have one thing in common. They're all rich in iron. So these are the minerals that crystallize and cool first. The minerals down here, such as quartz, muscovite, potassium feldspar, and the sodium-rich plagioclase, all of those have one thing in common, and that they're very rich in quartz. So these are the last minerals to crystallize. And yet, if you look at granitic rocks throughout the world, crystalline igneous rocks, most of them are granite. As it turns out, granite rocks form very massive rocks because of their rich quartz composition. So we have a lot of questions. And right now, certainly in the fields of igneous petrology and volcanology, we really do not have a clear handle on what's going on underneath the earth with respect to these magma bodies. We don't know on continental volcanoes if that magma body is going to erupt, that's going to be a quartz-rich magma body, or it's going to be an iron-rich magma body, or a mixture of the two. A lot goes on underground that we can't see. We have no way to go underneath and sample this. Only thing we're able to do is sample volcanoes. We do know now that when volcanoes, just prior to eruption, they emit a lot of sulfur dioxide. When they're in a more of a dormancy state, they emit a lot of CO2. So most of the volcanoes around the world today, the hundreds of volcanoes, are emitting carbon dioxide in the atmosphere right now as we speak. As those volcanoes get closer to erupting, that's when they emit the sulfur. And that's when you better say, watch out, it's getting ready to erupt. So these magmas mix, and we know that they are definitely two chemically distinct magmas. One's going to be iron-rich, which is going to be higher temperature. One's going to be a quartz-rich magma. If these two come together, they can form an intermediate magma. And that was the problem with Mount St. Helens. Mount St. Helens right now is still erupting. It's actually producing very dark mafic rocks. Now in 1980, it did the opposite. It produced very felsic, silica-rich rocks, very explosive. And I think we pretty much beat the different magmas to death here. So that ends igneous rocks. So if you need to know a little bit more, tune into the Zoom lecture. Zoom lecture is a little bit more informative. I give a little more hints on quiz questions. So this ends igneous rocks.